Hello AP Physics students, this is the second video for the Chapter 4, Unit number 2 on forces, advanced forces, and Newton's laws of motion. I want to pick up where we left off, talking about Section 3 in Chapter 4. This is Newton's second law of motion. Newton's second law of motion is just the mathematical version of Newton's first law of motion. So Newton's first law of motion basically talked about static and kinetic objects. Objects that aren't moving, or objects that are moving but not accelerating. Either way, you're looking at something that is related to net force. And in Newton's second law, we see the equation F equals ma, which is really an equation that's very flexible. It has two uses. It can be used for individual forces. Every individual force, like the force of gravity, or friction, or the normal force, or tension, or an applied force, any force you can think of, is the product of some particle being accelerated, so a mass and an acceleration. However, this can also be used on the larger scale to include more than one force, all the forces in either one direction, so the net force left and right, net force up and down, net force forward and back. So this is called the net x, net y, and net z force. Or it could be the total resultant net force, which is the sum of all the forces in every direction. So when you think about this, we really can have two applications for this equation, F equals ma. The actual wording of the law itself says, if a net external force acts on a body, the body accelerates. The direction of the acceleration is the same as the direction of the net force. The mass of the body times the acceleration of the body equals the net force vector. That's probably not how Newton said it, because there's a lot of verbiage in there that's more modern. But it basically says F equals ma. It's from this equation that we get the definition of the unit of force, the Newton. 1 Newton, unit of force, is 1 kilogram of mass being accelerated at 1 meter per second squared. So if you took a kilogram mass and you start pushing on it or pulling on it in one direction with a constant force so that it got faster by 1 meter per second every second that you pushed or pulled on it, then you're applying a Newton of force, which isn't very much force at all. Again, Newton's second law of motion can be broken into components. So there can be a net x, which is going to be the sum of all the forces in the x direction. It's going to be the product of the mass, the particle, times the acceleration, the net acceleration of the forces that are going to the left and to the right, no matter how many there are. There's a vertical version of this, and then there's a forward and back version of this. I highly recommend that you check out these active online physics activities by clicking on them on the e-text, the electronic version of your text on masteringphysics.com. Because I think when you do, you'll see a lot of applications for Newton's second law of motion. All right, here's a really good example of the application of Newton's second law of motion. Example 4.4, determining acceleration from force. You've got a worker, and this worker applies a constant horizontal force with a magnitude of 20 newtons. So he's constantly applying 20 newtons of force to the right, to a box that has a mass of 40 kilograms, and it's on a level floor, and there's not really any friction. What's the acceleration of the box? This is actually pretty easy to figure out. We can figure out from Newton's second law, F equals ma, that each force is going to be the product of mass and acceleration. Since we know the mass of the box is 40 kilograms, and it's on this planet where the acceleration of gravity is about 10 meters per second squared. It's actually 9.81 meters per second squared. Then we can say that the force of gravity is going to be the mass times the acceleration of gravity, which we usually just use g for. So it's going to be mg. So it's going to be 40 times about negative 10 meters per second squared. So we're going to have about negative 400 newtons of weight. So you have 400 newtons going down. We got 20 newtons to the right. What we know is that we're going to need, according to Newton's third law, which we'll talk about in a lot more detail later, in order for this to remain in equilibrium up and down, in order for the net force to remain zero in the y direction, if you've got negative 400 newtons pushing down for gravity, you're going to need 400 newtons pushing up from the floor. Otherwise, the floor is going to collapse underneath this thing or this thing's going to levitate up into the air. We know that it's not doing either of those. It's actually only moving to the right because the net force in the x direction is going to be the sum of all the forces in the x direction, and the only force in the x direction is the applied force. So we're going to have a net force of 20 newtons. Well, one important thing that you need to recognize about these forces, one rule that you can follow that's really easy, is if you know that Newton's first law applies, if you know there's equilibrium like there is in the vertical direction, then we know that the sum of these two forces is going to be the same. The sum of these two forces will be 0 because the two forces are the same. If you take the force of gravity down and you add the normal force up, they have to add up to 0. So they have to be equal and opposite to each other. So if one of them is negative 400, the other one has to be positive 400. But what if, in the case of what's going on left and right, they're not in equilibrium? What if we know that the object is accelerating in a certain direction, as Newton's second law says it should? Well then, instead of setting them equal to each other, we're always going to set them equal to ma, because the net force has to be equal to the mass times the acceleration in the x direction. So what we can do is we can say the mass times the acceleration in the x direction has to be 20 newtons. Since we know the mass is 40, then the acceleration is going to be 20 divided by 40. So it's going to be accelerating at about 0.5 meters per second every second. Pretty simple application. The key to it is, if you know they're in equilibrium, set them equal to each other, the net force is 0. If it's not in equilibrium, set it equal to ma, and then solve for a. All right. What about in example 4.5? What about in example 4.5? Well, can we do it the other way? Instead of determining acceleration from net force, can we determine net force from acceleration? Sure, it's still the same simple equation, F equals ma. In this case, a waitress shoves a ketchup bottle with a mass of 0.45 kilograms to the right along a smooth level lunch counter. The bottle leaves her hand at a certain initial velocity, 2.8 meters per second. Slows down until it comes to a stop. So it stops here. And it does that over the course of a meter. What is the magnitude and direction of the frictional force acting on the bottle? Well, we know that the free body diagram is going to show that the weight, the force of gravity acting on this, is just going to be the mass times the acceleration of gravity. They told us the mass is going to be 0.45, and we know the acceleration of gravity is about -10. So it's going to be about 4.5 newtons downward. That means that the normal force going up is going to be positive 4.5 newtons, because I already know that the sum of the forces in the y direction has to equal 0. That means the two forces in those directions have to cancel each other out. So the normal force has to be equal and opposite to the force of gravity. 4.5 newtons up has to be equal and opposite to 4.5 newtons down. Because the ketchup bottle isn't levitating off the table, and it's not collapsing the table. But what about what's going on left and right? Well, there isn't a force going this way, the direction the bottle is going, once the waitress lets go. Sure, there was some force there originally, but unless she's constantly pushing it, or constantly pulling it, or she straps a rocket to it, or propeller or something, the ketchup bottle isn't going to continue to accelerate in that direction. It's actually going to decelerate, because friction is slowing it down based on its initial velocity. Now we can go back and use a basic kinematic. We know the initial velocity, and we know the final velocity, we know the displacement. We don't know anything about time, which means we could use the no-time equation to figure out the acceleration. That's what they do right here. They say that the acceleration has got to be -3.9 meters per second squared. Once we know the acceleration is -3.9 meters per second squared using the no-time equation, and we know the mass, which is given to us, finding the net force is as simple as multiplying those together. And that's how they ended up with a net force of -1.8 newtons, because it's negative because it's pointing to the left, and it's the only force. If there was another force, then we would include it in that net force. But as it is, the sum of the forces in the x direction is just start naming all the forces in the x direction. Friction. That's it. And what is friction? Well, we know that friction is -1.8 newtons, so that's your net force. pretty self-explanatory, pretty basic, but you're going to want to practice some of these, and that's why I've given you some tutorials to try on masteringphysics.com. All right, let's talk a little bit about Chapter 4, Section 4. I've mentioned this a couple times now. Weight is the force of gravity acting on something. Please make sure you know the difference between mass and weight. Your mass never changes. Your mass is the same regardless of your location in the universe. Unless you lose a body part, get a haircut, disrobe, something like that, your mass isn't going to change. So if I tell you something has a mass of 50 kilograms, that's going to be its mass on top of Mount Everest, in Paris, in London, in Jackson Township, or on the moon, or in Jupiter, or near the sun, at least momentarily. So it burns up. So when you think about that, your mass never changes. So your mass is not subject to change. However, your weight is a force. Your weight is the force of gravity. It's the effect of the acceleration of gravity on your mass. So it will always be dependent on where you are. If you are near the sea level, it's going to be about 9.81 meters per second squared. If you're moving up away from the center of the Earth, it's going to be less. If you get up in space where you're practically weightless, it's because you still have mass, but you no longer have as much acceleration. If you go to the moon, it's less. If you go to Jupiter, it's more. So knowing actually how to calculate your weight is really dependent on where you are. So when you think about this, that's the key idea. That weight is dependent on location. Mass is never dependent on location. So let's think about the net force and acceleration of an object in free fall. Take, for instance, a coin. If you dropped a coin from the Leaning Tower of Pisa, and that coin falls freely, so the effects of air are negligible, how does the net force vary as it changes? Well, make a free body diagram. Just think about it. It's got the force of gravity acting down. There's no air resistance. The only force acting on it is the force of gravity. So it's going to be the mass of the coin, which isn't going to change, times the acceleration of the coin, which isn't going to change, which means its weight is not going to change. If you do take into account air resistance, it will change. Because as more and more air resistance builds until it reaches terminal velocity, you're going to continue to have the downward force exceeding the upward force, and so your net force is going to look more like this. Your sum of your forces in the y direction will be the force of gravity plus the force of friction of air resistance, and that always is going to be equal to mass times acceleration because we know they're not balanced until you hit terminal velocity. When you hit terminal velocity, your force up and your force down will be the same. This will be 0, which means this whole thing will be 0, which means the force of gravity will be equal and opposite to the force of friction at that moment. But until that happens, there will be a net force, and you have to solve for the acceleration. Here's another example of mass versus weight. You know, a Rolls Royce is traveling in the x direction, makes a fast stop. The x component of the net force causing it to stop is about 1.83 times 10 to the 4th newtons against the direction that it's going. What is its acceleration? Well, this is going to be a simple force of gravity equals mass times the acceleration of gravity situation to find the mass of the car. So you can use that to find the mass of the car. And then once you know the mass of the car and you know the net force acting on it, you could use it to find the acceleration. The applications for this equation are really pretty mathematically simple.